Yeah. And all of the content, most of the content is taken from the paper showing here, Theory of Graph Neural Networks Representation Learning. And because we only have 1.5 hours, so my presentation will focus on the first part, representation abilities. And so let me first give you the problem setup. We are, for graph neural networks, we are actually interested in solving analytical tasks on structured inputs. So for most tasks that are on structured inputs, we have two kinds of tasks. The first one is given a graph and we would like to predict its label. So the label is based on the whole graph. And the second part is, the second task is given a graph and several nodes or a pair of nodes, we're going to predict the node label or the node or the edge label. And for most of the graph neural network model, they can be written in a message passing flavor. So the message passing flavor basically considers is composed of two very important operation. The first one is called aggregation. That is to aggregate information from one node's from the neighborhood of one node through a nonlinear function f(phi). And after we got a message function, we are going to combine it with the node representation of itself. So this is called update function. And after we get this message, we'll aggregate it. From by its own neighbor, from its own, combine it by its own representation. And if this is, so here we get node level representation. And if we want to further obtain a graph level representation, so we aggregate all the node representations to a single representation called FG possibly through a nonlinear mapping. So here, mostly we are using, for example, a sum function followed by a MLP, for example. So this F sigma must be permutation invariant with respect to the node ordering. So this is the graph neural network formulation. And there are two very important properties of graph neural network model. The first one is we have to be permutation invariance of the node of the graph. That is to say, regardless how we permutate the input graph, the resulting graph representation should be the same, right? And the second property is equivariance of the node representations. That is to say, if we permutate the graph in some ways, the resulting node representations should be permutated as in the same way. So those are very important properties that we're going to talk in deep later.
So I have a question with 1.6. Is the equivariance, shouldn't there be a P outside of the F on the right hand side?
Oh, yeah. Oh no, here we actually this is the node feature, and we left multiplied with a permutation matrix, and we are going to still, this is because we write this permutation equivariance in matrix form. And if you look at it, if you write it in vector form, actually you have to multiply it with a permutation matrix. Yeah, here it is in matrix form, so it makes sense. Okay, regarding the theory on theoretical specs on graph neural networks, so we have n input samples. Usually they are identically and independently drawn from some underlying distributions, D, and D times Y. The Y is the label space, and we have several training samples, and we can calculate the so-called empirical risk based on the training samples. But because we don't have direct access to the underlying distribution itself, so we are actually caring about the so-called population risk or the true risk that measures the loss on the underlying distribution. So this will lead to several questions we are considering. So the first concern is that given a GNN model class F. So which target functions we can approximate by this by a family of GNN models? And the second problem is that, the first problem concerns with the representation ability or the expressive ability, right? And the second problem is called generalization. So even if we have sufficient or enough representation power, so we can only estimate the empirical risk. That is to say, we are very curious about how the empirical risk is, how close the empirical risk to the population risk or the true risk. So this leads to the problem concerning generalization. And the third problem is that we usually employ GN models on test samples that are from different distributions, right? So here a learned model is usually deployed on a different distribution Q, not equal to P. For example, in our molecular representation terms, we usually concern molecules that exhibit different properties in training samples and test samples. So in which cases we can expect successful extrapolation to Q, given that a model is trained on P. So this is the problem concerning with out of distribution generalization. Due to the time limitation, we are going to focus on the first problem in my presentation, and maybe some days later, I can share you the rest of the two problems. Okay, here's a very simple illustration of the problem we're going to introduce. And regarding the expressive power, so we're going to, so the outline of the presentation is, we're going to firstly recap the so-called graph isomorphism test. And based on the graph isomorphism test, we're going to know a family of or a hierarchical of representation abilities. And based on this hierarchical of representation abilities, there are two common approaches. The first is called node identities with local algorithms. And the second category of approaches we are going to introduce is called higher order graph neural networks. And based on the two approaches, we can obtain several theorems on the universal approximation abilities of graph neural networks model, graph neural network model. Okay, so what is graph isomorphism test? This is a typical characterization of the discrimination power or the representation power of GNNs. That is to say, given two graphs, can our graph neural network model identify whether they are isomorphic or not? Let me give you a example here. So actually we have, so for example, if the input to our algorithm is G and G prime, so it is very easy to find that G and G prime is actually the same graph, right? Except that the ordering is different. So can our GNN model recognize whether they are from the same, actually the same graph? So this dates back to 1968, the so-called, the two Soviet Union mathematics, they propose a so-called Weisfiller-Lehmann algorithm. And here is the simplest version, the so-called one-dimensional Weisfiller-Lehmann algorithm. So this algorithm actually aims for recognizing whether a given pair of graphs are isomorphic or not. And the basic procedure of this algorithm is that firstly, we're going to we initialize all the nodes with their initial color. So if they don't have initial color, we can actually color them in the same, we can give them one color for all of the nodes. And the second step is called refinement. The refinement is that we aggregate the color from one node's neighbors. And after we aggregate the neighbor, after we aggregating the color from their neighborhoods, we are going to use a hash function to map the obtained set to another color. So here, please pay attention to this function. This is actually what I mentioned is that it has to be a hash function in the sense that it should be an injective mapping from the input to an alphabet. So after we aggregate the embedding or the color into a new color, and we proceed to the first to this refinement step until we got a stable coloring. And after we terminate this problem, And we are actually seeing that whether all the nodes, all the remaining nodes are the same. So let me, this is kind of abstract. So let me give you a concrete example here. So suppose we have two graphs, G and G prime, and we colored all the nodes in red. And for this node, for this red node, actually it has two neighbors in color, right? So we map this, during the refinement step, during the aggregation step, we're actually obtaining a set that consisting of two red nodes, right? And plus its own red node. So actually, this is the intermediate representation for the top red node. And for this left side red node, because it has three neighbors, this one, and this one. So each representation should be like this, right? And similarly, we can compute every new colors based on this rule, and we will get two different kinds of representations. The first one is one red node plus a set consisting of two red nodes. The other is one red node plus a set consisting of three red nodes. And like I said before, we are going to map those representations in new color, right? So we give the first color, we map it to blue, and we map this color to yellow. So this basically finishes the first iteration, and we will get three blue nodes and two yellow nodes by the end of the first iteration, and similarly for G prime, right? And after the first iteration, we repeat the above approach, right? And for example, for the top blue node, we have two yellow neighborhoods. So right, and for this yellow node, we have one yellow neighborhood and two blue neighborhoods, and we will color them in. Okay, and for this for the left corner, blue one, we have one yellow neighborhood and one yellow blue neighbor, and for all of those three intermediate colors, we give them new colors. Okay, and by the end of the second iteration, we will find that if we give them new colors based on neighborhood aggregation, they will stay the same. So basically means that the distribution of the color won't change anymore. So we conclude that this algorithm can terminate. And after this algorithm terminates, let's see what's remaining. Okay, so after we terminate the algorithm, we will get final. Okay, so this in the end of the algorithm, we are going to look at every iteration. So for the first iteration or the input stage, we have 5 red node, right? So we calculate the histogram of the node color and with respect to its size, and we have one green node, and we have 2 purple node. We have 2 pink node. So resulting the representation, so the graph representation can be written in this way, and similarly for this way. And because of the 2 algorithms give the same, the 2 graphs will result in the same representation. So we conclude that G and G prime is isomorphic to each other. Okay, so any questions about this one-dimensional Phelan-Lehmann algorithm?
Can you define what is a graph isomorphism?
Oh yeah, the graph isomorphism is that given one graph, and we can arbitrarily permutate its order, right? Its node order, and we have to recognize whether this, for example, given one graph and we permutate arbitrarily its node ordering, resulting another graph, and let's see whether those graphs are still from the same graph.
Yeah, so I think isomorphism, right, is basically a bijection, right?
Yeah.
So permutation is like one side effect of something that's not like violating the kind of bijection. Right? So I just wonder if there is a mathematical
a general form of the isomorphism.
Yeah, like how do you define isomorphism? Is it like you can define an arbitrary bijective map between the nodes, or is that how it's defined?
Yeah, actually, this isomorphism problem is NP hard. So
So if you Google it, the definition is saying that you have two graphs. You can define an isomorphism on them if and only if two nodes were adjacent in the first graph after the mapping are also adjacent in the main graph.
Okay.
Yeah.
So basically, this is like saying no matter how you do the permutation, you always preserve the first half neighbors.
I see.
So because the graph isomorphism problem is NP hard, so this so-called one-dimensional with Wheeler element test is sound but not complete, which means that if one-dimensional with Wheeler element test output non-isomorphic for a pair of graphs, then they are indeed not isomorphic to each other. But if one-dimensional with Wheeler element algorithm outputs possibly isomorphic, that means that it is still possible that the the pair of graph is still not isomorphic. Okay, so this is one thing you have to keep in mind. And another thing I would like to mention is that actually here we are using a multi-set representation of the neighborhoods. So the difference between multi-set and the plain set is that we allow one element to appear multiple times in a multi-set. Unlike for a plain set, we just allow each element to appear only once. Okay, so this is the one-dimensional isomorphic test. So actually, it is very obvious that our graph neural network model is actually operating in the same way as one-dimensional with Wheeler element test. So and because of this kind of analogy to each other, so since the with Wheeler element algorithm uniquely colors each neighborhood, and we say that the coloring always refines the representation from a graph neural network model, and we will obtain the following theorem. The theorem is simply saying that if we can determine that from the output of a graph neural network model, the FG is not equal to FG prime, and identically, the one-dimensional with Wheeler element algorithm will determine that G is not equal or is not isomorphic to G prime. And how can we establish this kind of identical relationship? Is that so for any T is the number of iteration, there exists a graph neural network model such that the color CT is equals to the node representation HT. And a sufficient condition to maintain this kind of equivalence is that the aggregate, update, and the readout functions should be injective multi-set functions, right? So this, like I said before, if you for the neighborhood set, this is a multi-set function, and for the update function, this should be injective, right? Because it's essentially a hash function, right? So it has to be injective to the output alphabet space. And for the, this is node level, and for the graph level, we have to compare the multi-set. So comparing the multi-set, we are going to use another hash function, right? So the another hash function should be injective as well. So that's why you have to make sure your graph neural network model, if you want your graph neural network model to be equivalent to a one-dimensional with Wheeler element test, you have to make sure the aggregate, update, and readout functions in your graph neural network model are injective multi-set functions. So this actually gives some implications for distinguishing two graphs. So it actually, because it established an equivalence from with Wheeler element test to graph neural network model, so you can directly transfer any existing results for the one-dimensional with Wheeler element test to graph neural network model. And one particular example is that one-dimensional with Wheeler element test fails to test whether two regular graphs are isomorphic to each other, so that graph neural network model can't as well. What are regular graphs? The regular graph is that all the node degree is the same in the graph. So let me give you another example here. So actually, there is a input graph A consisting two independent connected components, and we have another graph G prime consisting 6 nodes, but they are connected to each other. And actually, when you run the one-dimensional with fill element algorithm on the two graphs, and it will give you the same embedding. But actually, from the two graphs, it's obvious that the input graphs are not isomorphic to each other, right? So this is the one case that one with fill element algorithm fails, because it can't give you it can't detect whether two regular graphs are isomorphic to each other. Okay, so any problems so far? Okay, let me proceed to my presentation. Okay, because in theorem 2.1, we requires that the neighborhood aggregation and the update function and the readout function should be an injective multi-set function, right? So how can we represent a multi-set function in terms of neural network languages? And here is another theorem showing that how to universally approximate multi-set function with for example, multi-layer perceptions. So the theorem states that for any multi-set function, multi-set function x less than this means that the input space is less than m to R to the real space on a countable domain x. So any function can be represented in this way. So this way means that we can, there are two nonlinear functions, phi1 and phi2, and phi2 is operating on each element of the set, and the phi1 is operates on the resulting intermediate level embeddings. And actually, this is what graph isomorphism network does. It implements this kind of sum decomposition in the aggregate function to ensure the ability of the injective operations. And there is one thing to note, that because this theorem is based on a countable domain, but actually in our neural network domain, actually we're dealing with these continuous domains, right? So there is a gap between the theorem to practice. And one implication of this is that for a graph neural network model, the latent dimensions D2, the D2 is actually the size of the inner representations. The latent dimension D2 must be at least the maximum degree of the graph. That means that you have to at least use you have to have a latent dimension that is larger or equal to the maximum the size of the neighborhood set. Okay, so this is the so-called graph isomorphism network, GIM. And another implication from the connection of one dimensional with fill element has to graph neural network model is that we are actually comparing its computation trees with the structure of the graph of the input graph. More specifically, right? What contains in an embedding computed by a graph neural network model is that we are going to build a so-called a computational tree that is an unrolling of the message passing procedure. So like the example here, when we compute, for example, the embedding of A, we are consider its first hop neighborhood B and C, right? And after we got this layer, and we are recursively build its neighborhood to the tree. So actually, when we are comparing whether the node representations are identical to each other, so we are actually comparing the computation tree of each node. So again, so this if two nodes are not identical to each other, then we have the computational tree based on the embeddings. Sorry. For two nodes U and V that is not equal to each other, but we have identical computation trees, then we conclude that their embedding will be the same. So again, one-dimensional with fill element test essentially colors the computational tree, and the comparing computational trees directly implies that graph neural network model cannot distinguish regular graphs, as the example shown earlier. And this kind of analogy from one-dimensional Wishfeld-Lehmann test to graph neural network model is another implication is that it also shows limitations with practical impact. For example, when we want to learn a combinatorial algorithms, or we want to predicting the properties of a molecule, because in molecules, the functional groups are very important, and usually functional groups are a subgraph level of the input graph. So basically means that some portion of the computational tree will resemble to each other. So in this case, the graph neural network model fails to distinguish between two functional groups. And we will give you some of the existing results from some literature. So here one paper. So you can click if you download my slides, you can click to the link here. So number 5, citation number 5, and the citation number 7. They are very famous papers that study some failed cases of graph neural network model. Okay, for example, in literature 5, it says that message passing graph neural network model cannot decide the girth. What the girth is the length of the shortest loop within a graph, and the circumference is the longest length of or the length of the largest loop within a graph, and the diameter of a graph, and the radius of the graph, and the existing of a conjoint cycle, and the total number of cycles, and so on and so forth. And in literature 7, it says that graph neural network model cannot count the induced attributed subgraphs for any connected patterns of 3 or more nodes. So here, it shows that a practical implication of this paper is that for some molecules that is consisting of a ring like this, so it actually cannot count the number of subgraphs within this kind of input graph. So those are some limitations of graph neural network model. So how can we go beyond those limitations? Actually, there are 2 main directions. The first direction is to introduce the so-called node identities. And the other one is to use higher order functions that is not operating on node, independent node, but are tuples of nodes. Let me introduce them one by one. The first direction is called node identity. So what is node identities? So when you look back to the computational rules of the graph neural network model, you will find that one major weakness of graph neural network model arises from their inability to identify nodes as the origin. Basically means that you don't know whether the message, where is the message from. You will only aggregate them all together, right? You don't look at the specific origin of each messages. So one very simple way to improve this kind of limitation is that we can add some numbers to the we can attach specific numbers with each message from the node, from the neighborhood set. And this will produces a bunch of related work. The first one is try to establish the connections with local algorithms, and there are some analogy between the node identities with some distributed algorithms. And another one is that we can actually randomly assign some node identities to each node. This will gives you a so-called high probability universal approximation of invariant graph functions. I will introduce this later. And another way is to, because we don't have unique identities in some cases, we can use some augmentation functions that incorporate some structural or features or topological features to the node attributes. For example, in some transformer models on graphs, you will have the so-called positional encodings, right? And some, for example, the Laplacian positional encoding and some random walk-based encodings. All of this works fall into this category. Let me introduce the local algorithm at first. So local algorithm is Okay, you don't need to know every details of those slides. You just need to know how we arrive at the conclusions. And if you want to establish some representation abilities to your model, you can try to connect your model to several of the directions I mentioned in the presentation. Okay. Okay, let me just step aside from the main topic, try to give you some motivation or the background knowledge of the distributed algorithm. So there is a kind of a very large kind of distributed algorithm is called local algorithm. So what local algorithm is this local algorithm is a kind of distributed algorithm where the input data defines the computational problem itself and the computational path or the network topology of a distributed system. So this local algorithm will proceed input regardless of its size. Unlike in usual cases, for example, when we give you an array of size n, and for example, you want to sort an array, and the maximum or the minimum time complexity will be O n log n, right? For example, so actually in the usual cases, in the non-distributed setting, the system will proceed the input algorithm of specific size, but in a local algorithm, every problem or every client will proceed only one problem at once, regardless of the complexity of the input graph itself. And more formally speaking, each node V is a computational identity or a client that computes a local output. And how we can finish the computation is that we will exchange the message to the node to its neighbors. So what determines the computational path is by edges, and we will use U and V belongs to the edge set, denotes that nodes U and V can communicate with each other, and each part of the output is determined as a function, right? Only consisting of its local neighborhood. So you will see that again, this resembles to graph neural network model as very obviously, right? And in local algorithm settings, we assume that there is a so-called a port numbering. The port numbering actually gives you the information of where the message comes from. For example, here we considering the input graph of three nodes, U and V, and we can arbitrarily number number one and number two to its side. It's just like the out source of the message. Okay, and the port numbering is not fixed. You can actually, like the graph itself, you can permutate the node port numbering in a flexible way. So for example, for a U and V, we can give port numbering in a picture A and a picture B. Okay, and once you have a general idea of what is a local algorithm, and we will briefly introduce the so-called distributed local model. So the local model dates back to 1980s. So this kind of model gives this is a computational model, basically saying that it will mimic. It is not the same. For example, the Turing machine as in our previous experience. This is another kind of computational model. So what this model works is that each node will perform their local computation. And after they finish their local computation, each node will send the message to the port 1, 2, 3 until the degree of its node. And after the node sends the message to each port, it will receive the message from the other side. And this 1, 2, 3 steps are executed in a synchronized manner. Basically means that it has to, after it sends the message, it has to wait until it receives a new message. Okay.
Sorry, I have a question.
Okay.
So, according to my current understanding, this port number is not a necessary part for a local algorithm.
It is necessary for the local model. So this local model, but it's not that necessary for the local algorithms, a family of local algorithms.
So what if I don't have this port numbers? I just do my local computation.
We
follow a random order to send out.
We will assume it exists. this is based on this is our assumption. We will assume there is, because this is a very abstract level of computation. We don't need to think about how can we make it happen. We just need to know. We just need to assume it will have every node.
Right. So in other words, if I don't have this order, can I still call it a local algorithm?
No, you can't. This is not assumption of this. It's a kind of weird, but actually it is. You can refer to citation number 16. This is a survey of local algorithms published in ACM computational survey and tutorials. It will outline several definitions of local algorithms. I just take pieces of them here.
It's just that intuitively, I feel like whether it's local or not versus whether it's ordered or not seem like two different things.
Yeah.
Yeah, but I will check the reference.
Okay. And
Yanqiao, before you're moving on, can you explain more about the port idea? Like, how does it come from? Is it like, I understand, like for example, if the node has 2 degrees, then we're going to assign 2 ports. Is that the case?
Yeah, that's right.
Then how to put that port? Like, for example, does one port associate with like just one edge?
Yeah. Every basically means that it will tells you how the port number will tells you how or where you are going to send message and where you are going to receive your message. So basically means that each node will each edge will receive a port number. Will be assigned to a port number.
Okay, and in your example, you actually gave 2 different ways to do the numbering.
Yeah.
Right? A and B, are they equally good?
Yeah, they are equal. They are equal.
So we just random assign a port number to each edge associated with each node.
Yeah, that's it. So the only difference between this computational model to our graph neural network model is that we will give a specific identifier to the message, right? Because we associate a number with an edge, and we will know where the message comes from and where can we send the message to.
Right.
Yeah. So it's very obvious that we can improve the representation ability of graph neural network model by identifying the message identities. So in this work, the citation number 8, we will besides the neighborhood message itself, we will going to add more features. In this case, is that we will attach the port number of the source node and the target node, port UV and port VU, right? Besides the message the node representations itself, and the remaining part just as the same of the graph neural network model. And this work proves that it will give representation ability improvement in terms of the identifying the graph isomorphism. And actually, this is one thing is not clear is that because you introduce the so-called node numbering, and the node numbering is not fixed, it's a very flexible way, right? So how can you still ensure the permutation invariance with respect to the node ordering? Here, I don't know how they do this, but the conclusion I just take from their paper is that they can analyze the representation ability through a so-called VVC model, the vector consistent model. I'm not an expert in distributed algorithms, but I will trust that it is true. Okay, and this kind of analogy allows you to transfer how can you represent approximation algorithms in a distributed environment to graph neural network model. So we have now so far we have 2 tools that establish the representation abilities. The first one is to via the Westphalian-Lehmann test, and the second one is to via local algorithms. And I think there is another paper that mentions how to improve the representation abilities. Is that we can, like Yizhou just said before, we can give node messages with fully unique identifiers. In this case, we will going to identify each port number, and the port basically means that the port number will not repeat it. there is a paper in citation number 718, and does this way. It augments the graph isomorphism network model with randomly initialized identifiers, and which will result a model that can decide the subgraphs that regular message passing graph neural network model and this so-called CPNGN model cannot do. For the details, please check the original paper. Okay, and because we established the equivalence between the local algorithms to the graph neural network model. So going further, we can make analogies to local algorithms with the so-called Turing completeness. Basically saying that we can based on this equivalence, we can compute any function that is a Turing machine that a Turing machine can compute. Because in a Turing machine, we are allowed to do the graph isomorphism problem, so we can establish this equivalence here. And there are two theorems shows the equivalence to the Turing universal local model to the graph neural network model. The theorem itself is very simple. If I have
one question, so the graph isomorphism problem, is it like NP hard or
it's NP hard?
It's NP hard, then how can you solve it with the Turing machine?
I think we can approximate this problem.
I probably want to comment that that's a very tricky question. So if it's just a graph isomorphism, it's kind of someone claimed they can prove that it's almost P.
Really?
Yeah. But if it's like subgraph isomorphism test, then it's gonna be NP hard.
Okay.
Okay.
I don't. Okay. Okay. Yeah. So for the theorem itself is fairly simple. If I have two functions that are Turing complete, and if I can improve the graph neural network model with unique node identities, then this class of graph neural network model and the local algorithm, the local algorithms are equivalent to each other. Basically means saying that if I have a function graph neural network model F, there exists a local algorithm that will give you the same output and vice versa. And another implication or another corollary of this theorem is that because we can actually give you the so-called asymptotic result. If you have infinitely large graph neural network model, basically means saying that your depth and your depth is at least the diameter of the graph, and the width is the dimensionality of each node embedding is unbounded. Basically means that it goes to infinity, and your graph neural network model can compute any Turing computable functions over the computational graph. But this is not possible, right? It's just an asymptotic result. Even if so, for the bounded case, the GN will lose its computational power, right? But there is another model called congest model that bounds the message size, and we can transfer some results on the congest model here as well. But I don't check the details of this work. The citation the work in citation 10 is published in iClear last year, and it's 60 pages or more. So if you are interested in the details, you can check that. I just pick the results here, and I don't think I need to explain the details here.
Yeah, before you move on, can you briefly explain what does Turing completeness mean?
Oh, the Turing complete is that a function that can be is computable in a Turing machine. It describes I think it's P, right? The algorithm falls in the category of P. I
mean polynomial.
I forgot what the algorithm teacher, the professor teaches in to
Yeah, I also forgot, so that's why I asked this question.
yeah. But if you are interested, you can I can search about this later and show what's our Turing Turing complete functions. Yeah, I kind of forget it. It actually bounds in the time complexity of the problem itself, right?
I vaguely remember like pointer and we can move ahead, or there's some very basic instructions. Okay.
Yeah. Let me share with you guys later. Okay. Those so far we are actually talking about many theoretical results, and here are some practical ways we can improve the graph neural network model. The first way is to give random identities to the input graph. This paper publishes in EJKI 2021, and the title of this work is called "A Surprising Result When You with Random Graph Neural Network with Random Node Identities to Graph Neural Network Model." Why it's called surprising is that because if you assign intuitively, if you assign random node identities to every node, right, and this kind of graph neural network model will lose its representation power because it is not trivial to see. It is still permutation invariant, but actually, surprisingly, it is. This paper claims that if you assign the node identities to the here, it means that you will use the node identities as the node features, and this kind of initialization, random initialization, will still yield graph neural network model that is still permutation invariant, but this is not in a deterministic manner. It's probably it is in a probabilistic manner, saying that while the outputs will be random, but the outputs for different graphs will still sufficiently separated with each other, and it will give you so it claims this theorem. The theorem is that you have a permutation invariant function g on the graph of size n, and for any fixed delta and epsilon equal to 0, there will be a graph neural network model f with access to a global radar function and with random node identities, such that the difference between fg minus and fg and the underlying permutation invariant function g, the difference will the probability of this event less than or equal to epsilon is greater than or equal to 1 minus delta. This is in a PAC learning language, right? The approximately correct, provably approximately correct language. Okay, if you take a Chen course, you will know what I'm saying here.
This is roughly just saying f and g, they are equal
with high probability. Yeah, they are close to each other with a very high probability.
So it's like saying for two functions, you are not sure about what they are doing, but on random variables.
One is the here the function g, the g in g here is the underlying function we are going to learn, and you will have a function f that is parameterized by graph neural network model.
Right. This is just saying if there is this invariant permutation invariant function.
Yeah.
And I can find an f, which is the neural network I want to learn.
Yeah.
That is
that can approximate to
approximate.
Yeah, that's right. Yeah, that's right.
So in reality, how do we do this assign random ID? Do we just like increment the node feature by one dimension? Like
it's possible, and you can also replace the node feature set with the numbers.
So you mean we don't use like say the original features?
Yeah. If because in some
this is sufficient, so you just use the ID.
Yeah. In some cases, for example, in many monikers, you don't have node features at all, or in some social networks, some benchmarks, you don't have node features, but you have a graph level label, right? So you just need to previously what we do for a node for a graph with no node features, we just randomly give them, for example, 1 as the sole node feature, right? But here we can arbitrarily assign some numbers to the node. This is this is one very interesting paper, and another serious paper is.
One quick question. So, do they have any like a relationship between the epsilons and deltas? Because you remember in packet learning they have like a sample size.
I see.
Gives you some like bounds and guarantees. Here is a very general statement.
Yeah, I think they. I don't check the original paper, so.
I think what you're asking is like a bounding question, but here the theorem is like an existence.
Yeah, you will have, but how can you actually learn this function? You don't. I don't know, right? There will exist one, but how can you, for example, using gradient descent to learn this function? It's not. It remains unknown. And for another series work that are not that theoretical, is called distance encoding or positional encoding or whatsoever. The idea is the same. Is that you can augment the node feature set with some features that contain the structural information. The first paper I'm going to mention is called Distance Encoding, published in New York's 2020. It actually does a very simple way to improve the representation ability of graph neural network model by augmenting the node features with some distance encoding functions. So this distance encoding function, you can just imagine it by some, for example, some random walk matrix or some shortest path distance or some generalized or personalized PageRank score. You just need to augment or concatenate the distance to the node features, and it will give you better better computational power of your neural network model. And some other models include positional encodings. For example, the widely used Laplacian positional encoding basically means that you just take the eigen decomposition of the Laplacian matrix, and you take the resulting eigenvectors as the resulting as the position information, and you concatenate this so-called Laplacian eigenvectors to the node features, and your representation ability will be improved with some theoretical guarantees, but I just omitted the details here. You can check the original papers later. So far, this is the first part, how we can relate our graph neural network model to a local algorithm by giving some identity information of the node or the message, right? Okay.
For this one argument with structural information for each node, we have obtained the feature with the conditional encoding. Is it guaranteed that you will not force the
what problem?
Like the because in the previous slides you introduced only with random identity.
Yeah. I remember there are two kinds of isomorphism problem. The one is just you take the structural itself. You only consider whether, in terms of the structural equivalence, whether the two graphs are isomorphic to each other. And the stronger one we'll consider is node features as well. Yeah, so here actually, because in some real world applications, we are not that strict to isomorphism. We're just because we have to take node attributes as well, right? So yeah, we're not that strict, but in practice, this kind of positional encoding or distance encoding will give you very significant improvements in terms of performance. Yeah, and this is the first direction, and the second direction is called higher order graph neural networks. This kind of approaches, the idea is also very simple. Instead of just operating the message function on the node level, we can consider, operate the graph neural network model on a set that is larger than just the single nodes. And there are some approaches taken so far. The first one is the equivalence of graph neural network model to some higher order graph neural network with Wheeler-Lehman algorithms, or some geometric graph neural network model that performs message passing on simplicial or cell complexes. And this is the first direction. And the second direction is the so-called linear equivariant networks that use parameterized neural network model to approximate the equivariant linear operations. They have shown very similar expressive equivalences to k-dimensional with Wheeler-Lehman test, but all of them suffer from very high computational complexity. So it has theoretical, but they have very sound theoretical results. Before I go into the details of each model, let me just give you a general description of a high level of higher dimensional with Wheeler-Lehman test. The so-called k-dimensional with Wheeler-Lehman test operates or give colors based on a tuple rather than a single node. Okay, and here we just give you a pseudocode or the how the algorithm works. Firstly, in the initialization step, we're going to label each node, or each k tuple with its atomic type. So what is atomic type? The formal explanation is very abstract. For example, if two tuples k s and s prime in the V and in a k tuple space, they will get the same color if and only if the mapping Si to Si prime is an isomorphism from the induced subgraph. Okay, this kind of explanation is very vague. I will give you an example here. So when we considering k equals to 2, basically means that we are not operating message passing on node. We are actually operating the message passing on the edge level or the arc level. So every arc will be colored according to whether they are an edge in the graph or they are not edge, and whether they are loop. The loop is that the arc will come to itself, right? So there are 3 atomic types for k equals to 2, and for some and you could imagine when k increases, the total number of atomic types will go exponentially, right? Anyway, it's not that important. We can focus on the refinement rule here. So the color refinement rule will be replaced by a more complex form. But it's not that complex. The only difference is that we're not going to take every single neighborhood node, but we're going to take every adjacent, tuple. Here, we'll use the notion W divided by I, which means that the tuple S in the position I will be exchanged by W. So here, when we express the S in a expanded form, we're actually taking the position I by W. And we can, let me give you another example. Okay, don't ignore the computational details. It's just too abstract. This perhaps is one example I can show you. Okay, just imagine we are going to look at the case when k equals to 2. Okay, and when k equals to 2, and we have this kind of graph. Maybe for you have this slide in your computer, right? Because it's kind of small in the screen. Anyways, for this kind of graph, we are going to we can write the computational form like for every 2 tuple UV, we will take the neighborhood every UW and WV adjacent to UV and take their representations altogether, followed by a mapping hash mapping function. And a concrete example will be, let's take a look at the arc 1, 2. Okay, the 1, 2 is here. And for every 1, 2, we are going to count, we are going to consider its neighborhood set. So what determines its neighborhood set is as follows. We will take a look at, for example, 1, 2, and another node here, 1, one, it should be one. Oh, okay. Forgive me. Okay, it should be 1, 2 followed by every other possibility, right? Because for W belongs to V, you will have 3, 4, 5, 6, 9, 8, 6, 8, 9, and you will resulting the resulting neighborhood set will be in this. It will be like this, right? Yeah. So one thing to note here is that we are not considering its real neighborhood set. Real neighborhood set means they have direct connections in the graph. But here we are going to count every possible node that constitute the neighborhood. The neighborhood here it's just a one element difference, right? And after this, so we are going to represent this in a multi-set function, right? And followed by the other, the mapping function that gives you gives every arc a new color, okay? And some terminology difference is that when I look the literature on the higher order Risk-Field element test, there are a bunch of terminologies that are confused to me. For example, some authors in citation number 19 and number 26, they distinguishes between higher order W Risk-Field element test and the so-called folklore Risk-Field element test, the so-called WFL test. So actually the WFL test and the WL test is the how you compute the neighborhood set. So in FWL test, you are actually taking you are enumerating every possible tuple S, followed by a neighborhood, followed by a multi-set function. But in WL test, you will enumerate every possible neighborhood for one tuple, and after that you will compress it with a multi-set function, and by then you will have every possible tuple, and you will have another multi-set function on top of that arithmetic. Okay, this is kind of vague, but the only difference is that it because it involves actually two-dimensional computations, right? So it just determines that when you will use the multi-set function on top of the tuple representation. Okay, you don't need to know about those kind of details here, but actually the only thing you'll remember is that there are differences, and actually FWL test is stronger than FL test by one dimension, basically saying that the KWL, the k-dimensional FW test is equivalent to k+1 Risk-Field element test. And how can we mimic this kind of operations with graph neural network model, right? This is the focus of this is today's focus. And here we can actually organize every input, because nowadays we are going to represent the tuples in represent the input in tuples, right? We can organize all the input data in a tensor function. So the tensor, this tensor is actually dimensions is n times n times n for k times plus the input size dt, and the first k coordinates index the tuple, which is the embedding of the tuple S in layer T, and for for the input for the graph neural network model that use the node and edge information, we will shape the input data into a tensor as well. So how can we shape this tensor? We will going to use its first D channels that for the node attributes. Basically means that for every node and its D-dimensional features that equals to x. X means the initial features, and otherwise for u and v that is not connected in the graph, we just play padding 0 here. And the first channel, this is the channel 1 to D, and for the first channel we will record it the adjacency matrix. Basically means that this is the node feature. This is the feature level, and the second one is the structure level information. We can use this way to represent a graph in a tensor form. And after we have this set up, we can have a general form that that operates on this tensor. So this tensor, this is the shape function is just I mentioned you shape the input graph in a tensor form, and after that you will have multiple equivariant network layer that is message passing, right? You have to respect to the node orderings or the tuple orderings. And for that, you will have a reduction function because you in the previous steps you will have tuple representations, and you have to compress the tuple representations into a representation here. So basically means that for every node V, you have this kind of S tuple that begins with V, and you will take the sum of all the tensors here. So basically means that you take one dimensional off from the tensor and get the resulting representations for node V. And after that, for every V, you will apply another MLP function to just change its dimensionality, right? This is kind of this operation is kind of complex, but okay. Imagine that you have a two tuple. Your model is focused on two tuple, and for the first for the first T layers, that is of F1, F2, so on until you have Ft. It just operates on the tuple itself, and after you transform the tuple representations, you will have several tuple representations, right? But for our case, we are still interested in node level representations. So we have to convert the tuple representations into node representations. So that's why you have a function SE here, followed by a nonlinear transformation M. For this is the previous slide concerns with the node level embedding, and for a graph level embedding, we are going to use we are directly use a reduction function in this form. So it's very simple. You just take every tuple and take the sum of it, and you will get a graph level embeddings, and followed by a non-linear transformation M. So the only so for most of the higher order graph neural network model, the only difference lies in the design of function F, because it operates on the tuple level, so it has to be permutation equivariant, right? It has to respect to the ordering, and we are going to introduce two representative models in this category. The first one is called 123 GNN. It is published in AAAI 2019. So the idea is very simple. So far, we introduced the high-level order GNN, right? And it will instantiate its model by k equals to 1, 2, and 3, and it will operate a pooling function on the resulting 1, 2, 3 GNN and compress it by a MLP and obtain the final representations. And here to reduce the computational complexity, right? Because you can't actually enumerate all the possible tuples. It uses a weaker notion of k-dimensional WL test. It's called the set KWL test. So the test, the KWL test, the set KWL test is that you will construct a neighborhood set in this way. So that this way, it's very simple that you only have a one element difference from the original tuple, okay? And you will, oh, okay, this is the only difference. And after you construct a neighborhood set, you just need to aggregate every tuple from its neighborhood set, and followed by a nonlinear function mapping. And this model just you can again, okay, for this arc, this k equals to 2. So what is its neighborhood? It's just to take one element difference, right? Because you, for example, you fix this this point, and you will get this one and this one, and fix this point, and you will get this one, this one. So this is a weaker notion of the Westphal element test, but it will reduces the computational power. And similarly for the three tuple, for example, in this way, and you will have, if I fix this point and this point, because you have only one element difference, right? And you will have this one. And similarly for this one, and oh, there are not so many neighborhoods because yeah, right. There are not so many. This is the only this is the only neighbor you have for this 3 tuple, and similarly for this graph. Okay, you can imagine the difference here. And actually, this one is works very good in terms of efficiency and performance improvement and efficacy.
I think it's a very interesting idea, but like, what happens if you keep increasing k? Would that be like you end up with like a one giant tuple of all the nodes, right?
Yeah, but you will have limited neighborhood set because of you only consider you only think concerns with the set KWL test, right? But in our previous explanation, you will enumerate every possible tuple neighborhoods, right? But here, because you can't really do this, so it will.
So it's incremental based on your starting tuples.
Yeah, that's right. It's just like a search algorithm, right? You just find the neighborhoods that has one element different from your original tuple. Yeah, actually, this one works very good, and this paper receives for about 700 citations so far. So this is very interesting paper, and also this is the original paper that considers a higher level graph neural network model, and and this is not that important because through the illustration, I think you will understand the details. And another famous work that mimics the FWL test is in this way. So this paper, I remember it published in Europe 2020. It is called with Filler-Lehman test go higher or something, and it actually wants to mimic the expressive power of the k-dimensional with a 4-color WL test. So what he is trying to do is that for this kind of tuple, right, it try to enumerate every possible combinations. So what he's going to do is that you will multiply every in an element level, in an element-wise manner. You will multiply every k tuple representations that is different from you, right? And after that, you will aggregate the node level informations from every k tuple, followed by this the same update rule. And here I can give you some intuitions why it has to multiply the representations. Is that because for a node that is k tuple, you are actually if I consider k times 2, right, it actually will compute because remember in the construction we introduced earlier before, we encode the adjacency matrix in the tensor, right? And for k equals to 2, I can multiply the adjacency matrix by itself, so it will give you a squared, right? And for a squared, and you can use a function that computes its trace, and for this trace actually gives you the diameter of the graph. So you can, in this way, you can actually distinguish it from 2 graphs that are differ in the diameter. So this is why it wants to use the multiplication over every k tuples. And regarding its technical implementations, I think this is fairly straightforward. You will have 2 MLPs. The first 2 MLPs will operate on the FI function, and after that you will have another MLP that operates on the update function. So that's it. And right, you can look at this figure. You have 2 embeddings, and you multiply them by M1 times multiplied by M2, and you have another M3, and you just concatenate them together, and that's it. So far, okay. It's kind of abstract to introduce those strategies, but we'll have a short summary here, followed by the citation number 27. We are going to use the equivalence relations to describe the expressive power of the higher order graph neural network models. The equivalence relations here means that if I can distinguish G from G prime, if I cannot, I will give them isomorphic relationship. They will be classified as the same, and they will falling back to the same output space. And the aforementioned GNN families will have the following equivalences. The general message passing graph neural network model is equivalent to one-dimensional or two-dimensional with Wheeler lemma test, and the K-set GNN is equivalent to K-set K-dimensional set with Wheeler lemma test. And for the paper I just mentioned before is called LEG GNN. LEGN is equivalent to K-dimensional WL test. And for the folklore GNN is equivalent to K plus one dimensional with Wheeler lemma test. So it will actually building a hierarchical of representation abilities. And some similar results can be obtained for equivariant models. Equivariant models means that you are going to compute the node representations rather than graph representations, which is except for this paper. Okay.
So Yanqiao, I have some questions.
Okay.
So theoretically, of course, KWL, right, is like more capable, more expressiveness.
Yeah.
And also this like hierarchical structure about expressivity is very interesting. But I just wonder from practical perspective, right? So in those papers, do they provide evidence like some graph problems for the real world data set? Actually, this kind of high order WL tested graph neural network actually can produce better results in terms of, for example, accuracy.
Yeah, they do. Most of the benchmark data sets they use are focused on monikers, and actually for those molecular property prediction tasks, they all exhibit some extent of some sort of performance improvements, but they don't give some explanations that based on that, because molecular properties are very complex. They actually most for the illustration purposes they use toy data sets, but when in terms of the empirical performance they use molecular data sets, but they don't explain why the molecular data sets improve.
Okay, so do you think some sensitive data set might be helpful? Because even for molecule, I guess most of them just a graph level classification or regression problem.
Yeah.
But for some graph problem, for example, I think in the earlier slides, you mentioned that the K-click problem is a very tough problem, right?
Yeah.
If we create those, like we know, like from graph perspective, they're a hard problem, and then they try to prove the effectiveness of this high order WL graph neural network, probably that would be more convincing, I guess.
Yeah, actually there are some works that target at a specific combinatorial problems, like as you, for example, the K tuple, but I don't include this in my slides, but they do have some.
Okay.
You can check out the survey paper. They have mentioned some combinatorial problems that can be solved in higher order graph neural network model.
Yeah.
But I believe they have very limited practical values, because the real world data sets are far more complex than those concrete problems. So actually most of those problems are very theoretical.
Yeah, but at least we know some graph problems that are very hard, right? NP hard problem.
Yeah.
For the molecule one, it really depends, because even we're interested in graph level property, but some of them can be easily tricked by just looking at, for example, the node label distribution, then probably already answer the question, right? So if we want to show or demonstrate, or like number-wise, if we want to see some significant jump, then we need to find the right class of problems.
Yeah, I agree. Okay, and because I think the time is only 6 minutes left, so let me finish this problem. The remaining technical we are going to introduce is called linear equivariant layers, right? So if you look back the general form of the high order graph neural network model, you will find that here, you will find that actually this has nothing related to the message passing itself, right? Especially for those F functions. You can actually use linear equivariant network layers to approximate those network to mimic the message passing layers or the message passing mechanisms. So that this inspires a family of so-called linear equivariant networks, especially the citation number 23. So it actually, so in this work, the KLEGN linear equivariant graph neural network model, what it does is that it will replaces every function f with a linear function L plus some, for example, some sigmoid function that is non-linear, but it's actually it acts in a coordinate-wise manner. And also this kind of sigma function can also be replaced with far more complex, for example, an MLP that gives you more representation abilities. A family, and also this work actually characterizes all the possibly invariant and equivariant layers that show that there is a universal approximant theorem. The thing is that if you can build a full basis of all the possibly linear and linear invariant and or equivariant networks, because they have some dimensions, and actually you will and your space will be the similar as the other. Your space will be your space will be fully representing for all the possible linear equivariant and invariant functions. Yeah, and also the results shows that this kind of construction will give you the fully similar or fully equivalent expressive powers as the k-dimensional WL test. So this is basically means that this is another way of you can do the higher order graph neural network model just by multiplying several linear layers. And okay, there is also a so-called universal approximation problem, but I'm afraid that we are running out of time. But the idea is very simple. There is a so-called Stone-Waitress theorem showing that you can translate the previous expressive hierarchy in terms of WL test into the universal approximation results. Right, this just translates the WL test expressive to some universal approximation results. But I'm not going to introduce this in details. Okay, here are some concluding remarks. So actually, what we have talked so far, the first one is that we learn how to characterize the representation abilities of graph neural network model through the lens of graph isomorphism test, right? And we have two different tools to demonstrate higher expressive abilities. The first tool is through node identities by mimicking some local algorithms, and the second one is to build higher order graph neural network models that operate on tuples rather than just the nodes. And there are some limitations. The first one is that we don't talk about some spectral graph neural network models. All the GNNs we talk today is message passing graph neural models. So for those spectral models, we can borrow some existing results from the signal processing community to the representation ability to GNNs as well. And we don't talk about the adversarial robustness and their computational scalabilities and some some approximations. And there are also some questions that we can think for our future work. The first one is that because we have limited representation abilities of graph neural network model, which motivate higher order GNNs, but they are actually computational expensive, right? Can we build some theoretical results for the efficiency based on some, for example, we can use some sampling techniques to reduce the complexity, right? How can we build some? How can we still obtaining some theoretical results for those simplification? And the second problem we can think for about is that most real world applications that do not require fully graph isomorphism power. That means that in some real world cases, even if the two input graphs are isomorphism to each other, but you have different node features, and actually their labels will be different, perhaps will be different. that's saying that this means that you don't need to build a model that has fully representation ability power or the KWL power for larger K. So and actually, when for all the papers I introduced today, they don't use K larger than 4. Most they focus on 1, 2, and 3. Another question is that can we how can we come up with some other measures of the representation power that make sense, especially in some application, real world applications. This is this is what I'm going to think about for, especially for the monikers. We can use some other real world applications to demonstrate the representation power of the graph neural network model. And can we give some better results or some very sound or technical solid technical results based on those results, based on the representation power. And also, the only one take-home message of today's topic would be you have to really consider about the complexity versus expressive power. So there is a trade-off, especially you are going to use those models for your real-world applications. You have to think for whether it's necessary to use the fully powered graph neural network model or just some simpler or some weaker model, but they will perform better on your data sets. And that's it. Here are some references you can take a look at it later. Yeah, and I think this survey gives you a very sorry, let me switch to the first page. I think this survey gives you a very high-level picture of what's going on in terms of theoretical aspects of graph neural network model, and for the generation and the out of distribution generalization problems, there are not so many works that can fill into a reading group. So maybe we can find some next time to introduce them later. But if you have some questions or you are very interested in this, you can discuss with me. I'm also still learning many of the concepts here. So if you have some questions, we can discuss together. Okay, thank you.
Thank you, Yanqiao. So just want to confirm that time complexity wise, the KWL algorithm actually is kind of n to the power of K. Is that right?
Yeah, it's actually exponential to the K.
Yeah, but polynomial it's kind of choose K out of n, where n is the total number of nodes.
Yeah, that's right.
So that's why it's kind of n to the power of K, roughly.
Yeah. Okay, so see you guys tomorrow. Sorry, on Thursday.
Okay, thank you.